Hi friends, how are you? In this one, we're going to illustrate the definition of a subspace. Let's just read through these. Take a look. It says, a subspace of a vector space, I'm assuming you already know a vector space, what that is a subset of V with three specific properties. The zero vector of V is in H. Let's stop for a second and let's illustrate this. So what I'm going to do is I'm going to construct a little picture here on the side. This is going to be in 3 dimensions. So this is an axis this way, an axis this way, and an axis going up. Look at the first part. It says the zero vector of V. So if this is V, right there, all of this 3-dimensional space, then the zero vector of it you could indicate by just the point 0, 0, 0. But I'll just write it symbolically as 0 and I'll place an arrow above it. So this is the zero vector of V, right there in that position where the axes meet. Let's throw in a little dot to represent that. Make it, say, green so it's a bit more interesting. So that is located right there. So now look, the zero vector of V is in H. So the way we draw H now has to contain that little dot. So we can do that by drawing a plane essentially. An object that looks like this. You're going to have a piece going this way, say, a piece going this way, a piece kind of this way, and a piece this way. And notice that it contains that point, the little green dot. In other words, it contains the zero vector of V. So you think of V as the larger object, and H then you think as the smaller object here. Alright, let me move the V so it doesn't seem like it's referring to just the red object, okay? It's kind of out here, this way. So that's one basic fact. The zero vector of V is in H, right there. What I'm going to do now is look at the next part of the definition. It says H is closed under scalar multiplication. What I'm going to do is I'm going to take this, I'm going to make a copy of it, move it down, and we want to be closed under scalar multiplication. So we can illustrate that part of it by doing the following. Draw a vector, say within H, because it says H is closed under scalar multiplication. So draw a vector in H, say that's a vector in H right there. That's an arbitrary vector. It doesn't have to be that vector, it could be a billion other vectors within H, okay? And then it says it's closed under scalar multiplication. What that tells you is the following, that what you can do is you can basically scale it this way, look. So for example, this green one is a scaled version of the black one. And as you can see, it's bigger than the black one, but it's still contained within H. So that's what this part means. H is closed under scalar multiplication. When you produce a scaled version of a vector, it doesn't, for example, leave H. Go outside it somehow. Let's do the last part. Again, I'm going to make a copy of this picture here. And the last part looks like the following. It says H is closed under vector addition. That's the most complex of the parts. In other words, we need 2 vectors to do this process. So let me draw 2 such vectors. I'm going to use this arrow. This is one vector right there within H. Grab another one here. So I'm going to represent that, say, by a blue arrow, also within H, you see? And now we apply the basic principle of vector addition. So what we can do then is use the parallelogram method of vector addition, essentially. You take that vector, you make a copy of it, and then you displace it parallel to itself, and you place it at the tip of the other one. And you just want to make sure that the result of adding 2 such vectors produces a vector that lies within H and it doesn't go off H. So in our case specifically, if I did that, let's see. Let me use a color, like this grayish color right there. You see, that's the sum of the 2 vectors. See? So here, let me throw some symbols. I just kind of gave you a bit of the geometric interpretation. So some symbols we might, for example, refer as follows. Back in the middle picture. So this right there, let's say that the black vector is called V. And the green vector is some kind of scaled version of it where you multiply it by a number that changes the length, but it doesn't change the direction of it. So usually we indicate it by C times and then V this way. So C times V is a scaled version, as you can see, right there, of V. If C, for example, is more than 1, then you're stretching it. If C is between 0 and 1, then you're shrinking it. C could also be negative. That would basically just flip it and make it point in the opposite direction. Looking at this one here, so I'm going to have 2 vectors when I look at this one. I'm going to have a vector A. So maybe let's call the black vector here vector A. And let's call the blue vector, I'm going to call that B. Let's call it B, right? Like that. That's the blue vector. And then, oops, let me grab that again. There we are. And then the grayish vector would be the sum of the 2. So you would say it's A plus B this way, right there. And notice that it is meant to be confined to that plane defined by the red line segments. So these are geometric interpretations of some of these basic definitions. And that is it. So if it's been helpful and insightful, friends, please leave a like and subscribe. Thank you so much for watching. I'll see you in another video.